Anyway, here's my redstone calculator. Uh, Made completely out of circuitry, zeros and ones. So I guess I'll just demonstrate it. There's one. Now it's going to do a 3. So you got 13. And that actually is going, it's encoding into binary and decoding. That's one of the reasons it takes, that's one of the reasons why it takes so long. But I'll demonstrate that later. Do plus, wait until you get a 0. And it's actually storing that 13 in RAM as a binary set. We'll do 26. Oh, we got the 2. Equals. $39. So it's exactly what we wanted. So I'll reset this. And I'll start showing how it works. Okay, so in Minecraft you get ors and you get knots, and those are the only statements you get. And torches is how you negate a statement. So this is a 0, and the 0 charge gets transferred to this block right here. So when I click on, the block becomes charged, the torches turn off, and then you get the negation. So when I flip this off, this turns back on. When I flip it on, it becomes the negation. Now, this is pretty obvious. So, okay, so this is both off. So this becomes off. This is on. So it's on again. Since one's on of the 2 in an order statement, the whole statement becomes true. Same thing on this side, and same thing if they're both down. And it's basically the order statement. Any joining of 2 redstone circuits, I guess you could say. And this is the AND statement. A little bit more confusing, but not too bad. This, it negates it with a not, negates it with a not here, makes an OR statement, and then there's another not statement. So once this is negated and this is negated, this turns on and it represents the AND. So when I click this torch gets flipped back on, this becomes a not, because this block as a whole becomes a 1, so this becomes not. And I'll show you on the other side, so does the same thing. And if you both of them, yeah, same thing. This becomes charge in the not statement. And that's basically your AND statements, which, all you need is AND and ORs to do any logical statement. So that's why I can build a calculator. So this is memory. So this kind of holds a charge on one side or the other, and it has to do with timing. For a second it turns off, and then it gives a chance for this to power up and then make this block charge so it can't get repowered after it. So you can think of it, it basically functions as memory. To reset it, you just hit this block, and that block will do the same thing it did to this block, except for it just comes out and around and then charges this. This becomes an 0. That gives this the opportunity to turn on, and then this, once this gets turned on, this can't get turned off again. So it basically functions as memory. It'll take one shot of positive electricity or ones or whatever, and then it can switch values. But that's basically all you need for the calculator. So I'll start by just putting in 1 and following the stream all the way to the display. So 1. So it actually, where's the 1? Right here. So 1 starts right here. It gets found. Wow. Kind of a mess here. 1. Okay, 1 is the outer. Oh no, it's not the outermost. It's just the second most outermost. I forgot what side was 10s and 1, so I'll just follow this out. Okay, this must be the 10 side, because this must be the 0 place. The 0 place in the 10s. So this must be the 1 side. Yep. So you can see right here that this is opposite of this. So this is like I guess I'm using the 0 to be representative of this line being activated. So you follow this line, and then you find that this torch is off. It's using a modified version of the AND gate, because by default the first digit you put in, a 0 turns on, so it's 0, 1, so it becomes 1. So the signal gets transferred. And this is where all the bits are stored. So you can tell that this is 1, because it has a torch in the 1 place. I go over to the next one. Yeah, a little laggy. It's a 2, you can see, but it's off. Only 1 will get turned on at a time. But if you continue going down this row, this becomes a 3, a 4, a 5, a 6, a 7, an 8, a 9, and then you go up here, and it becomes so this would be 10 right here. So it's a 2 plus 8. So yeah, that's 10 right there. But you go on so on and so forth. I've pretty much made a grid, 0 through 100, which this isn't a good way of doing it, because for every number that you had, you have to add one more binary representation. I actually made another calculator in the future that has a log n. So for every 1,000, you have to do 10 more. Is that log n? I'm not sure. But for every 1,000, you only have to do 10 more. But anyway, so you have this 1 activated. This is the binary representation of 1. You follow it. And this gate is just, the top one is the equals gate. The bottom one is just displaying it on the, when you initially enter a number, displaying it on the display. And that, when you click equals, that's when it'll display this top one instead of this bottom one. And I'm using AND gates to do that. So since the 1 side is on, this side right here, the left side of each one of them, since that's always on, it won't get represented until I tell it to do otherwise. But anyway, we'll come to my decoder. This is actually how I store my I store it into memory. After I click equals, or after I click plus, and I add another value, I need a way of retaining the value of the last one. So that's right there. I'll show that a little bit later. So you go here, and this is I call it a decoder. I don't know if that's right, but anyway. So let me think of how this works. I think this is working off the negation. Okay, so yeah, you need to, in order for the number to get represented, you need a negation of the statement. And the only way to get the negation is to perfectly match up the ones and zeros. So, which one? This must be the 0. Okay, so I remember how I did this. So this represents a 1, and each one of these torches are a negation of the statement. So they represent a 0. So, 0 or 1, 0, 0, 0, 0, 0, 0, 0, all the way down the line means that this is the one that's going to get represented on the like the graph, so to speak. This is pretty much the same exact setup as the encoder, but it's in order to get the right combination, it has to be exact to the right number. So, for instance, this is the second one right here. Anyway, so this is 1. This is actually 1 all the way up. It's 1, 11, 21, 31, all the way up to 91 at the very top. So this gets a 1. It comes right here. And then it goes to my display, which I have 1 for the left side, 1 from the right side. And I've got that broken down into 1, 2, 3, 4, 5, 2, 4, 2, 4, 7. Into 7. So you have top, top right, top left, middle, bottom right, bottom left, bottom. And in so each one of these is the code to it. So the 1 code, one of these must be the top right, one of them must be the bottom right, and that gets transferred up into here, and that's how you get the 1. So we'll just we'll add 1. We'll kind of explain what's happening. Or no, I'll add 2. Alright, we're waiting for this to deploy. 2. So I'll show how that memory worked. Come on. There we go. So now the 2's deployed instead of the 1. And what happened is this is a more direct route compared to going all the way around. So a signal gets sent here, it resets the memory first, and then this signal gets transferred in memory. It's already being the adding units that I have set up. So I'll go ahead and click equals. Equals. So it's going to add the 1 and the 2. The 1's already stored in the memory, the 2's already on the line. So the way my calculator works is it's already set to be determined, the equals. And it's just this top row. So it represents this top row instead of the bottom row. Which you can see it's these 2 that are getting represented, and 1, 1 is 3, which is what we needed to do. And that is accomplished by these adding units that I have set up, which they're really cramped together, so it's kind of hard to see the logic. So I made a gate over here. So when you're making adding units, the things you have to consider is you're going to get a remainder. You could get a remainder rather, and you have 2 inputs, and you need to get one of 4 outputs. I think you need, if there's no remainder and nothing going in, you need no remainder and no remainder, and you're not passing on a 1 or a 0. If one of them is up, you need to pass a 1. If 2 of them up, you need to pass a remainder and not pass a 1. And if all of them are up, you need to pass a 1 and pass a remainder. So we can just test out to see if the 0 works. And no remainders being outputted, no 1's getting outputted. This represents the 1 or 0 that's getting outputted. This represents the remainder. So what if we want 1? So I've broken this up into 3 things. I basically made 3 logical statements, and off those 3 logical statements, the 3 logical statements are the only 3 that you need in order to determine the value needed. So we have A, B, or C. So if any one of them are lit up, this lights up. We have, this is AB or AC or BC, and I have this hooked up. So what basically happens, you have ABC, all 3, these 3 right here, and you have an AND gate here between that would be A and B. You have an AND gate between C and B right here, and then you have an AND gate between C and A, and all of those get wired together in an OR gate right here. So if any 2 are on, it lights up, and we only have 1 on right now, so thus far it's working. And then the last one is A, B, and C. And this is the torch that would represent it, and it's not on, so we know that it's working. and that's just a three-way AND gate, pretty much. So what we need for, if we have 2 on, we need to show that it's not getting carried over. Or actually, I didn't even show the first one yet. So the first one, it goes through here. You get A, B, or C. And then this is kind of added on, but you need A or B or C and not AB or BC or AC, which is this one. So I have, this is the negation right here. And since since it's not any of these, and it is A, B, or C, it's true. So this is why the output would be 1. And notice that it doesn't matter if the remainder put it over or if it was one of the two values of the two binary numbers that you're given. So we have 2, we just need the remainder and not the we need the remainder and not and a 0 being represented. So because this is A or B, well, we have A or B or C, that's true, but it's not true. Either AB or BC or AC are true, and that doesn't satisfy this not statement. So a 0 gets represented here. But there is a remainder, however, and the remainder can pretty much be hooked up all by itself, because if you have any 2, you're going to have a remainder, and if you have all 3, you're going to have any 2, so you're also going to have a remainder. So this can get wired directly as the remainder. And lastly, if all 3 are on, if you give a remainder and then both the numbers you're adding up have a 0 or have a 1 in this particular placeholder spot. Now, this is still going to be false right here, but that's alright. This is already true because AB or AC or BC are true. In fact, all of those statements are true, but you just need 1. But you needed to have a remainder with 3 1s going in. And then the logic here is A or B or C and not AB or AC or AB or AC or, oh, I got that mixed up. A, B, E, C, B, C. That's wrong, but whatever. And or you could have that all front part could be not true, or ABC, which this is true when you have all 3 up, and because this all gets negated. And you have, that's what you needed to show. If you had 3 things, you needed a remainder and a 1. So that pretty much wraps it up. This is just a more spread out version of this right here. But yeah. Yeah, that pretty much covers a quick run through of how my calculator works with circuits. So peace out, I guess.